Hello, testing. There we go. Okay. Hi, everybody. Welcome back to the latest train wreck that is a Deep Astronomy live stream. My name is Tony Darnell. We've had some doozies here, and I know what you're thinking. Let me just get it out before we get too much further. You're wondering, I hope he doesn't get real negative Nelly like he did last time. Last stream, kind of said my piece, kind of said my what was on my mind about, I don't know, quite a few things, not just terraforming Mars, but also what I thought of a lot of humanity's abilities to get things done. I've got that out of my system now. So today we're going to talk about space-based telescopes versus ground-based telescopes. Which one is better? And I'm actually going to have an answer to that question toward the end of my little stream. So let me just point out that I am streaming on YouTube, Twitter, Twitch, and Facebook. Only one guy ever watches me on Facebook, and that's Dennis. So welcome, Dennis. I don't get more viewers on Facebook because you got to pay Mark Zuckerberg money, so I don't get a whole lot of views there. The largest comes from Twitch, and followed by YouTube. So I am able to see all of your chats though on all of those things, and I can do things like show your tweet here or show your chat this way. Hello and welcome from Ontario. Is that are you Toronto? Are you in Toronto? So welcome. We also have Dan. Dan sometimes shows up. He lives up in Canada as well. So welcome to everybody from Canada, also from Europe. Most people seem to be watching me from Europe because of the time of day. It's the middle of the work day here in the United States, and everybody's working. At least they should be. So most people that watch me is in Europe and other places. So you can interact on Twitter or chat. Feel free, go right ahead. But the funner way to do it is to get on the Deep Astronomy Discord server. I think I put an invitation in the description box. So I hope I did. If you've already a member, though, just join in. Click on the live stream voice channel, and you can get into the stream. You can just talk. Now, I'm not wearing my earphones right now because if I were wearing them now, I could hear anybody that's in there right now. And if they talked or had their mic live or whatever, it would distract me. But when I get done with my little thing here, I'm going to turn that back on and you can be a part of the conversation. That's fun because we can chat, we can talk instead of me just reading chats all day long. So, Denmark, yes, welcome. Welcome, Denmark. It's good to see you. I'm glad that you're here joining us. Architufus is on Twitch, so that's cool. I'm glad that you're here also. And Neil from Deep Astronomy or from YouTube, Critty is also on YouTube with us as well. So welcome to all of you guys. The format goes something like this. I'm gonna pick a topic, something I think is interesting, something I think you want to learn more about. And I do a little bit of research and I put together some slides. Thought somebody came in there. And I show you those slides. I go through them just to give us something to talk about. And then I look at the chat and we can go over it. Okay. Today's topic is about ground versus space telescopes. Next week, I already have the live stream already picked out. The topic is going to be JWST. Is it too big to fail? Now, whenever I ask these questions, I'm actually going to give you an answer. This isn't clickbait. This is something we're going to talk about and hash out and go through and decide. And it's going to be binding. What we say in these hangouts matters. If you make a commitment in a Deep Astronomy hangout, that's just the way it is. It's kind of like when the International Astronomical Union decides Pluto's not a planet. That's the way it is. So, binding. These are binding arbitrations, so to speak. Susan Hunter, it's good to see you also. Dr. Lungworm from Twitch, it's good to see you. Welcome, everybody. Yes, fellow Florida person. But we're the good ones, right, Susan? Oh, God. The news from Florida. Okay. So I think that's all of my spiel on the beginning part of all of this. If you want, I also stream on Tuesdays. Just a quick note for those of you, I don't stream on YouTube on Tuesdays, but I do everywhere else. And I might add YouTube if you guys want it there. But next Tuesday, T Cubed, I'm probably not going to stream. Well, no, I'm not going to stream because I've got to go to Miami. So just a programming note. No stream next Tuesday. That's for people like Laxia and Peter and et al. Okay, so what do we got here? Let me pull this up. My little slide-o-rama. So I want to talk today about, we're gathered here today to discuss telescopes. In particular, this is from a professional setting, although if you're an amateur astronomer, this is also going to become increasingly more relevant because there's going to be a choice, not in the too distant future, where amateur astronomers can use space telescopes as well. So I would point your attention to places like SpaceFab et al. These companies are building large little or small little CubeSats, putting them in space. But anyway, professional telescopes is what I'm here to talk about primarily. Okay, so let me get my cursor in the right place and let's get started. First, let's start with some of the basics. I know you guys know a lot of this stuff, but let's go ahead and just go with it. Ground-based telescopes, well, goes without saying, I guess, but I'm going to say it anyway. They're located on the Earth's surface. They're designed to work primarily where the atmosphere is transparent. And we'll talk about that a little bit in just a minute. They're usually reflecting telescopes. That means that they have a primary mirror that reflects the photons that it collects up into a secondary mirror. But that wasn't always the case. Back in the early or the late 19th and early 20th centuries, a lot of the telescopes, professional grade, were 20-inch, 40-inch refractors. And so, but nowadays they're almost all reflectors because with a mirror, you only have to worry about a perfect edge on one surface of the glass. Whereas in a refractor, if you have a 20 or 40-inch piece of glass, it needs to be perfect throughout. So, and these days you would need multiple elements to make that happen. So they're not practical very much for professional use. So as a result of the fact that they only need one surface to be perfect, the side that has the reflective coating, they can be huge, huge telescopes. But they are wavelength limited. They can't see, because of the atmosphere, all wavelengths. So that's a disadvantage. Space-based telescopes, on the other hand, they're in orbit or they're in cis-Terran space. That's around the Earth, like L2 Point, for example, for Webb. And I'm even going to include lunar telescopes in the space telescope category. Okay. But I won't really say much more about lunar telescopes until this, because I'm going to save that topic all by itself for a future hangout. So that'll be a topic. In fact, I better write that down. Lunar telescope hangout. Okay, so they have the distinct advantage of not having to deal with anything in the atmosphere, and they can see all wavelengths that ground-based telescopes cannot see, and they can be in a variety of configurations. They're not necessarily reflectors, but most of them are. But how they reflect the energy depends on what wavelength they're looking at. If you've ever seen the Chandra Space Telescope, which is designed to sort of pseudo reflect X-rays, can you imagine how hard it is to reflect an X-ray? And compared to, say, Hubble, which reflects the much shorter or much longer wavelengths, there's quite a difference in configuration there. And of course, with anything that has to do with space, these things are enormous. So the cost, I mean, how much they cost. Okay, if you don't remember any other slide that I show you here today, remember this one. This I got from ESO, and the Earth's atmosphere is what will distinguish whether something is used in space or whether it's used on the ground. This is a graph. The brown areas are marked by the transmission percentage, and then on the bottom along the x-axis is wavelength. So on the y-axis it's transmission. So if you see something that's 0% transmission, like you do on the far left side of this graph, that means those wavelengths cannot get through. May as well be a brick wall at those wavelengths. Now, It's good for us because life on Earth probably wouldn't exist if these wavelengths, can you see my cursor? Yes, kind of. If these wavelengths here that I'm ranging over here were if they could get through the atmosphere, life on Earth probably wouldn't have had much of a chance. So it's a good thing that the Earth's atmosphere blocks these wavelengths. These are things: cosmic rays, X-rays, gamma rays, UV, all the way up. Here's UV radiation right up here where it starts to plummet. And then this is where things get interesting. You start to see a lot of valleys and all kinds of little structure going on in various parts of the atmosphere. Right here in this region where you see the rainbow, the atmosphere is transparent. And that's where we put a lot of ground-based telescopes to operate in these wavelengths. And then things get kind of weird. Around here, you get little windows where you can see things in the infrared. In fact, the 1 micron range and right around just a little to the left, I'm sorry, to the right of this observatory icon, you can do a lot of really good infrared ground astronomy if the location is right. And that's why we locate ground-based telescopes in places that we do. Places like Mauna Kea in Hawaii, Cerro Tololo, Cerro Peron, and all these other places in Chile, in the Andes Mountains. They get a lot of this because they are very dry and they are relatively transparent in the infrared. But as you can see, it's kind of hit and miss over here. Now, up in space, here, this is a picture of Chandra way up here. So it's operating in the short wavelength range. Here's Hubble. Hubble happens to duplicate a lot of what the ground can do. That's why in the 2009 servicing mission, they made Hubble primarily an infrared telescope, because why do up here what you can do just fine down here? So now Hubble tends to operate around this 1 micron to 10 micron range in here. And JWST, the next generation of space telescopes, is going to operate from about 1 micron all the way up to about 30 microns. So it's going to go way, way out here somewhere. And that is an extremely important area for scientists who want to learn about the early universe. So JWST is not in this picture, but it's going to be roughly right around in this range here, almost all of which is opaque here on the ground. And then, of course, it gets really transparent at long wavelengths where the radio astronomers live. They live in this wavelength range here. And then, of course, around 10, 20 meters or so, the wavelength range, it gets opaque again. This is where ALMA lives, is in this region here. And one of the most promising new areas of astronomy, and ground-based astronomy anyway, is in the radio, particularly with things like with the ALMA and the upcoming Square Kilometer Array. They show the universe in high-resolution radio wavelengths, which is something we've never done before. And it was one of the telescopes, in fact, it was the telescope, I would argue, that made imaging the black hole event horizon in M87 possible a few years ago. It was because of ALMA was part of it. They used other telescopes around the globe, but ALMA was the heavy lifter in that. So remember this graph. If you don't remember anything else, this brown stuff may as well be a brick wall when it comes to optical observatories on the ground. Okay, so, or I'm sorry, well, any kind of telescope on the ground, but mostly optical. Okay, little couple words about resolution. This is the only math you're going to have to see, and I even put it in a really busy part of the background, so it's hard to read. Telescope resolution is the single biggest thing that we worry about next to wavelength coverage. And it's defined as the ability of an optical system to separate 2 point sources. Okay, the angular resolution of that telescope is put out by this little thing here. It's about equal. The angular resolution is about equal to 1.22 times lambda over d. That's the wavelength over the diameter of the objective. Or another easier way to put it is just say that the resolution element in radians is equal to the wavelength over the diameter. There's the relation. So what you need to, it's sort of a back of the envelope thing. It's a little more complicated than this if you want to get into the details, but by and large, this is how you know you can figure out what resolution element you can expect from a given diameter at a given wavelength. So if you know the wavelength you want to observe and you know the resolution that you want to observe it at, you just solve for d, and you can get the diameter that you need to build to be able to do this. And so anything that is larger than the angular resolution of a telescope is called an extended object. Things like the sun, the moon, we can generally resolve this greater. Generally, it's greater than the angular resolution of the given element. But you can go further, and you can say, well, how many resolution elements can I get out of, say, a square meter on the moon, for example? And then you can see more and more detail. An example is, if you've ever looked at Google Maps and you have the satellite layer on, and then you try to zoom in, well, whatever took that image up in space can see the trees pretty well, can see houses and even cars, but it gets real fuzzy when you try to zoom in on, say, a car and read its license plate. It can't resolve that small. So, but to do that, you would just need a bigger diameter telescope, and you'd be able to do it. Anything smaller than that is considered a point source of light, a resolution element. All right, so that's all we got to worry about with resolution. So let's compare some objectives. This is how, in fact, I don't know how readable this is. This one, I may need to do this. Let me try. Let me put this up, and let me just put that up, and oops, let me go up. Go up. There you go. Oh, man, it keeps going down again. Shoot. Well, it won't let me. Let me do this. I see what I want. I know what I want to do. I want to do this, and I want to do this. Oops. There. Now let's just stay there. Here is, I know this is a busy graph, but here's a comparison of all of the different diameter mirrors that are going to be built or have been built in the past. We can go way, way back to the top left of this, where you can see the Yerkes Observatory had a 40-inch lens. That's what I was talking about. That's down here. So these are some of the first really big telescope mirrors or lenses to be built. And then, of course, there are other. You can see the Palomar telescope is here at 200 inches. The Hooker telescope at Mount Wilson is here. So you can kind of get a sense of how these different telescopes come along. Some of them are really large, like the Hobby Everly telescope, the one in Canary Islands, the Gran Telescopio Canarias is here. There's two Keck telescopes that look a lot like JWST mirrors. And then, of course, we see things that are being built now, like the 30-meter telescope, which has been delayed, but that's what it looks like. The extremely large telescope, the ELT, has also started construction. Here, this is cool. This is the Vera Ruben Observatory. This is a survey telescope. It used to be called LSST, and it's got a really bizarre primary. The main light collecting area is an annulus, and then in the center of this, it's got a different figure that's designed to give it an extra wide focal length to see even more of the sky. So this is a really interesting telescope. And of course, the Giant Magellan Telescope is here. And look down to the lower left here. We've got little tiny Hubble Space Telescope right there. It's been in orbit since 1990. And of course, James Webb is going to be up a little bit higher, a little bit larger than that. And of course, for reasons I'll never understand, we need to see the size of a tennis court and a basketball court. For some reason, this is the units in which we measure primary mirrors. So there you go. There's a basketball court here and a tennis court over there, because we need to know that to compare these mirrors to. But these are all of the different sizes that are out right now. And then and this is really funny. So we have the 30-meter telescope, the extremely large telescope, the Giant Magellan Telescope, and now we have in this big circle here, we have if you can see it in the background, the overwhelmingly large telescope would have this diameter around here. And then, of course, down here's a couple more. There's the Arecibo Observatory, which fell down. That's its radius right there. And the And then, of course, the Chinese telescope down at the very bottom says the 500-meter aperture spherical radio telescope. This is built by China and just came online. There's its radius down at the very bottom. So that's pretty cool. And let me go back to my thing here. And I'll do this. Okay. So those are some of the examples of the various objective sizes. All of them are done with the resolution in mind that I was talking about earlier. So what are the advantages and disadvantages of space telescopes? Well, the advantages are they can see any wavelength. Anything you want to see up in space, you can see. If you could build a reflective element for it, you're not limited by the opacity of the atmosphere. Your resolution is limited by the optics that you can build, not the atmosphere through which you have to look. That's great. They are really good for detailed high-resolution work. The field of view of the Hubble Space Telescope is very tiny. It can see an area of the sky of a grain of sand held out at arm's length. That's how much of the sky the Hubble Space Telescope can see, which is, as you can imagine, very, very narrow. Okay, it'd be some telescope differences. The way I like to describe it is space telescopes are like looking at the sky through a straw as far as field of view goes, and ground-based telescopes are more like looking through a paper towel tube or a kitchen towel tube. You can see way, way more of the sky than you can through a straw. So those are the different kinds of, that's short focal length, which lets you see more, and long focal length, which lets you see less of the sky. But you get higher magnification and you can see more detail for your given resolution element. Now they are astronomers' version of a point and shoot, right? They're not designed to look at big areas of the sky, with the exception of WFIRST, which is coming online, which will see a wide area of the sky. Telescopes like Hubble and James Webb Space Telescope, they're all going to be able to see just a tiny area of the sky at one time, and you've got to decide what you want to look at. So an astronomer would say, you know what, I want to observe the Andromeda Galaxy for 10 orbits, and here's why. And then the scientists in charge will look at that and go, okay, that's a good enough reason. You can have 10 orbits. Here's your schedule, and here's where you can get your data. Now leave us alone. So then they go to the next point and look and shoot that, and they go to the next part, and then they move around that way. So that's the way they're usually operated. But they have the disadvantage in that they really cost a lot of money. Anybody who's followed JWST for any length of time, and you know how much that thing's cost, $9.5 billion with a B dollars. Holy crap. What the heck did that money go to? But that's what they cost. Let's just not go into the fact that it was probably mismanaged at all by all those idiots building the thing. Still, even if it had been its regular, it would have cost $1 billion, which is more than any ground-based telescope tends to cost. So there's still a lot of money. They have relatively short missions, too, compared to ground-based telescopes. Hubble notwithstanding, it's been up there for 30 years, but it's been up there because it was designed to be repaired by the space shuttle. We no longer have the space shuttle, so repair is no longer an option for anything we put up in orbit now. But because of that repairability, it's been up there for 30 years, repaired 5 times, completely new telescope all the way around. That is not going to be possible with JWST, and I'll talk about that next week. So they're not easy to repair and upgrade. They're not good for long-term surveys because they just are too much in demand, right? Everybody wants to use these. They don't want to hog up a lot of time. The Hubble Space Telescope, when it took the Hubble Deep Field, was the first time anybody had used a telescope at one time for as long as they did. And that was done using something called director's discretionary time. At the way Hubble time is allocated, 20% of it goes to the Space Telescope Science Institute's director, and he can decide to look at whatever he wants to look at, or she can decide whatever they want to look at with the Hubble Space Telescope. And back in 1995-96, they decided they wanted to look at a small area of sky near the Big Dipper for 11 days. And boy, that caused a big stink. because everybody's like, what are you doing? You're looking at some blank spot of the sky nobody cares about. We need this telescope. But they did it anyway. And of course, the Hubble Deep Field is a result. Big gamble, though. And that's going to be hard to justify with JWST. So that's a disadvantage, in my opinion. Ground-based telescopes, what can they do? Well, they can have really large diameters. You saw that graph. Those were some big mamas, okay? And they're much cheaper to build and operate, on the order of hundreds of millions of dollars instead of tens of billions of dollars. So they are much cheaper to build and operate. They can last for a very long time. Keck and Subaru and the telescopes that are on Mauna Kea now were built in the early 90s, late 80s, right? They've been around a long, long time. So then their mission can last for decades and decades. We can get to them, we can repair them, we can upgrade them, all of that kind of stuff. So that's really a big advantage. And I'm going to get to this point in a minute, but they can be designed for very specific science goals. Not all telescopes are good for everything, right? Sometimes you want to build a telescope that's only good at one thing. And the example I'm giving there is the ExoLife Finder telescope. That would not be possible to build as a space telescope. And I'll come back to that in just a minute. So their disadvantages are, well, the atmosphere. It's all atmosphere related, right? They can't see all the different wavelengths, and in order to get to the wavelengths it can see, sometimes you got to get to some really strange locations, like high in the Andes, or in the valleys of Puerto Rico, or in the mountain, extinct volcanoes on Hawaii. And there's all kinds of problems associated with that. They're hard to get to, and that's always been a problem with ground-based telescopes. So I want to use the ExoLife Finder as a great example for what ground-based telescopes can do. This is designed by a group of people, and among them is my friend Jeff Kuhn at the University of Hawaii. This is an amazing telescope that's designed not as a general purpose telescope. It's designed to look for life and for signs of life in the nearest planets in our galactic neighborhood, and for nothing else. It's got a unique design that isn't good for anything else. It's got 16 5-meter off-axis primaries that go in a circle like that. Here it is, another picture of it. And each one of those primaries go up to a secondary, which then feeds down into a system of electronics that puts these images together. You get a wide diameter objective at the cost of these 5-meter objectives. And what's cool about this is they're going to be 3D printed. This won't be, as I understand it, using optical glass. So this telescope is on order of $100 million, I think, $150 million for the. Actually, this is the ExoLife Finder. This is the scaled down version of Colossus, which is the next level up from this telescope, which will have that ring filled in of more optical elements. So the ExoLife Finder, I think, is less than $100 million to build, and they want to do it in a private way to look for life in other planets. Here's another picture of it'll be an F-15 system. It's got 16 5-meter elements that go around the side. And check this out. This next part's going to blow you away. This is what they're going to be able to do with a telescope like that. This is from the ground now, mind you. Svetlana Berdugina and Jeff Kuhn developed an algorithm that will take the data from ELF and be able to resolve the surface of a planet around another star. And to prove that it works, what they did was they imagined that ELF was somehow installed at Alpha Centauri. What would the Earth look like from ELF using this algorithm? And then you can see that in the center there. You can see that, this is from Alpha Centauri now. And you can see the resolution, that you can begin to see the continents. You can certainly tell the difference between continents and oceans. You can also tell the difference between desert and forest, and all of this stuff, whether it's got vegetation or rocks, all of this stuff is going to be vital information we're going to need if we're going to try and characterize these exoplanets as anything remotely similar to the Earth. You can't do this with the Giant Magellan Telescope. You can't do this with the 30-meter telescope or the obnoxiously large telescope. It's going to have to be using a system like what Jeff Kuhn et al. have developed. So that, to me, is extraordinary. And this is on the ground, can be built now using technology that we currently have. And of course, for an example, for a space telescope, I got to do JWST. I'm not going to go into JWST because I've talked about it ad nauseum, but we know it's going to be launched in December. It's finally finished after decades and decades of delays and cost overruns, and it's going to go up, hopefully, when all is said and done, and look like that. And it's going to go to the L2 point, or Sun L2 point, where it will follow the Earth in its orbit around the Sun and show us the early universe. It is exclusively an infrared telescope. I told you it goes from about 1 micron to almost 30 microns. That's going to be its wavelength range, and you cannot do that from the ground. It's got a large enough objective so that it can actually, it has enough resolution that it can resolve planets around other stars. And it'll be able to do that because it's also got on the detectors, it's got micro shutters, which will block out the light from the star so that you can see directly the reflected sunlight from any planets. It won't give you that resolution element that we saw with Svetlana's stuff, but you will be able to see whether it's, its color, its size. You'll also be able to, with near spec, which is a spectrometer on board, you'll be able to see what is, if it has an atmosphere, you'll be able to see what's in it. So JWST's got a lot of capability. Most of it you cannot get from the ground. So this is a good use case for a space telescope. So let's get to it. What is it? What's the best? Is it the ground-based telescope or a space-based telescope? I'm just going to tell you right now, it's ground-based telescopes. And Jeff Kuhn convinced me, using ExoLife as an example, the ExoLife Finder as an example. I think ground-based telescopes are better because of a whole host of things. Yes, you're going to be limited by some wavelengths, but look at what we can do if we decide to scrap the idea of building general purpose ground-based telescopes and instead build special purpose ones like ELF. Then we get a lot more capability. You can work on them in the ground. They're cheaper. That you can tailor make them to the science needed, just like I just said with ELF. The atmospheric problems are becoming less and less of a problem, especially with resolution capabilities, right? You're never going to be able to see, certain wavelengths through the atmosphere, but you're not going to, seeing limited is going to be a thing of the past very soon with adaptive optics and other things like it. And so I think this allows for more innovations because when you build a space telescope, you end up having to use proven technologies. Now, JWST was different, and that's also one of the reasons it was so far behind schedule, is that they had to invent stuff to go into space because it didn't exist yet. So in their favor, or in their defense, a lot of stuff in JWST did have to be innovated. But they don't tend to do that too much with space telescopes because they are so expensive. But you can do that kind of thing on the ground. You can build a camera, see if it works, doesn't work. You're out a few, tens of millions, maybe $100 million, and you go back and do it again. But compared to the billion-dollar scale, that's quite affordable. So resolution will soon compare to space telescopes, as I just pointed out. We can see the surface of another exoplanet from the ground using ELF. And a big part of the future of astronomy is going to be in something called surveys. And these are things like Vera Ruben, where Vera Ruben is going to come online here in about a year, and it's going to look at every at the entire sky, the whole sky, every few days. And the amount of data coming from Vera Ruben is going to be just redonk. Okay, it's going to be so much, right? And I also think that we're going to need some AI capabilities to get through some of that stuff. But that's going to come online soon. Surveys, we need to be able to stare at big areas of the sky for a very long time, and that's something that space telescopes aren't very good at, because We want to see things like comets. We want to see asteroids. We want to see things that might hit the Earth. And we want to see supernovae explosions and microlensing events and all these kinds of things. So, that's it. I think ground-based telescopes. Okay, I got through that. And I'm now going to start looking at the chat. Let me get rid of this off of my screen. And let's see. Oh, there's some people. Oh, Tony, you're back. Okay. Let me make sure I have my audio and video set properly on this. I forgot to check that real quick. Voice and video, input device, and the output device. Yeah, okay, good. All right, let me put this on. Okay, good. Now, so Tony, I think if you say something, I should be able to hear you. You're not live yet, though. Okay, cool. All right. Let me get. Hang on.
Jwst myself. I really can't. I mean, it's going to allow us to see into the infrared, and I know that we can't do that from
That's right.
Earth-based. And I think that space telescopes have their place. And I think if it works, if it doesn't blow up on the launch pad, it doesn't screw up in the deploy, and we actually get some images off of that, I'm really looking forward to that.
Yes, let me be clear about something. The question was, which is better, ground or space? And I think ground is better. But there, of course, is a place, or has to be a place, for space telescopes. That includes going to the moon and putting them in lunar craters and all that kind of stuff. So yes, there always is a place for that. I agree.
Yeah, that's it.
It's just, it's just cost, right? So the kinds of things that we can do now, 3D printing is going to open up, I think, a lot of resolution capabilities for ground-based telescopes. Certainly, the algorithmic possibilities are well developed. Svetlana and Jeff et al., those guys have built some amazing software that really need the ExoLife Finder to show us these things. So I hope it gets built. It's all trying to be done in a private endeavor right now, because NSF and those places in America, it's the National Science Foundation that tends to fund things like this, and I don't think they've got the money, and I don't think there's enough of a community out there that want this yet, because astronomers are funny about life in the universe. They'll talk about it. Exoplanet scientists especially will talk about it, but only so far as discovering other things. They won't or in the line of exoplanets, which is now as an accepted field of study. 25 years ago it wasn't, right? So now it is, and now there's all these exoplanet astrobiology is a new thing as well. So now, in the context of that, people are wanting to talk about it, but try to do something that that astronomers like what's the guy's name from Harvard? Avi Loeb did with Oumuamua, and you get some serious kickback, right? So this is a funky area, but I do think that imaging and resolving planetary surfaces is going to be vitally important if we want to get any idea of what these exoplanets are like, whether they can even have any kind of biosignatures, technosignatures, whatever you want to call it. We need this kind of capability. So, but yeah, it's a good point. And I agree. I mean, I want JWST as much as you do. The infrared is where the interesting stuff is in the early universe. So we have to have infrared capability and to be able to see the very first stars, the very first galaxies, this period of reionization in the universe. All of this we need JWST for. Okay, let me get to, and by the way, if you just want to chime in and say something else, go right ahead. Let me get to some of the chat here. I'm going to see some of the things here. Charlie from YouTube. Yes, but the resolution from the ground will probably always be limited to small fields due to the atmosphere. Maybe. I mean, looking at large areas of the atmosphere it's going to be hard to compensate for that, like with adaptive optics. I agree with you there. However, if you take reasonably short exposures, and the larger the diameter you have, the shorter your exposure can be, you can minimize a lot of the atmospheric seeing. You won't get rid of it entirely, but it depends on what you're trying to do with this data. In wide field surveys like LSST or Vera Ruben, what you're trying to see are transients. You're not trying to resolve planets, right? Or double stars or any of that. You're trying to see transients, and you want to see as much of the sky as you can, so that you can see like asteroids going across, a supernova getting bright, a micro lensing event where a star kind of gets bright and dim real quick when something moves in front of it. Those are the kinds of things LSST wants to look for. It also is going to have a spectroscopic component to it, the precursor of which was the Sloan Digital Sky Survey, which gave us the first 3D map of the universe, large scale structure of the universe. So that kind of information is going to really expand us a lot. So again, it depends on what you want to do, and that's what you can do with ground-based telescopes, is you can narrow down your focus. Wide field telescopes aren't going to be good for zooming in on Eta Carina, but they are going to be good for looking for transients in the night sky and then telling other people where they are. Go and check out all these supernovae that we would have otherwise missed. So, Juan, I will add that launching something into space is risky. You never know if it'll blow up or if it'll arrive in orbit in good shape. Amen, brother. I mean, I don't know what you're going to be doing from December 18th until 6 weeks later, the end of January, but I'm going to be sitting here with my sphincter puckered because it's going to be a tough 6 weeks getting that thing deployed. So I hear you, man. It's all kinds of things. There's only about 9,900 things that can go wrong. So Cryptolicious, yeah, man, you got to check out. It's planets.life is the name of their website. I don't know. I had a hangout with them a couple years ago, but I have hangouts. So if you want to see Jeff talking about this and Svetlana, check out the hangouts that I've done. I think it was 2019. Watch them, man. It's amazing stuff. They go through all this stuff in detail. Okay. So eBone from Twitch. Now we're not taking into account the thousands of amateur scopes used for science. That's right. That's a software issue, isn't it? You could take all of this data from amateur telescopes and combine it into surveys, into transient studies, all kinds of other things. And that is an area that I think will only get better. People like asteroid hunters, Mike Forstner, who operates a wide field telescope from his home in California, contributes asteroid data to the Atlas survey. Mike Akey has a plane wave telescope that he uses to follow up with TESS observations with, and helps confirm the exoplanets that TESS lists as a candidate. So yeah, man, the growth of amateur astronomy into the professional realm is a big growth area. And this is from Neil, but we would never have seen what the Hubble deep field captured from ground-based. Maybe in 95, 96, and even later when they did the ultra deep field in 2005 or 2004, 2005. I don't know though. I mean, 30-meter telescope pointed at an area of sky, that's pretty good. I think it's going to get down to some pretty tiny magnitudes, 22, 23 magnitude. That'd get the early universe with it. Not in the infrared. Well, there is the infrared problem. You're right about that. So we won't see them very bright and visible, at least. And it'll depend on where in the infrared you can look. So yeah, okay. Because of the infrared problem, though, not because of the resolution element issue. So you're right. Also, I want all the greater observatories built, especially LUVOIR. Yes, LUVOIR is it's a next generation telescope, space telescope. It comes after JWST, which would come and after WFIRST, which is the Grace Roman telescope, which comes after JWST. It would be after that. Launched sometime in the 2030s. Probably not. Probably 2040. Anyway, it's big, right? Compared to it dwarfs JWST. So let's see. This is from Bullshit Vendor. OLT would have resolved down to you mean ELT would have resolved down to the milliarc seconds. Yes. Oh, thank you, Galaxia. Yes, go to the Discord there and join if you want to get into the live stream chat. Right now, only Tony's in it, but you can chat if you want. So we are in the portion of this stunt where we read the chat. Raj Luthra, but that would change when space exploration becomes easier, assuming it does. When is space exploration going to get easier? I think I get what your point is. I should probably scroll back up a little bit further. Very true. A large imaging survey. Still, if you look at the instruments on most ground-based telescopes, they are dominated by spectrographs. Right, right, because these they can look at. In particular, the spectrographs are used for things like the HARPS instrument on ESO on Sarah whatever it is. Forgot the mountain it's on now. Anyway, they're looking at the wobble of a star as it goes, as a planet orbits around it, and that requires a spectrograph to do it. And that also requires a lot of time because these planets have orbits that could span months, right? I mean, in our case, the Earth orbits the sun every 365 days. You can't justify having a space telescope looking at one star like that for 365 days. You can justify that with an instrument like HARPS, which can look at that star all you want and measure that wobble. And that's another big, I think, advantage to ground-based telescopes. I'm going to scroll a bit way up here because I've missed a lot of things. And I'm talking about things in reverse.
Can I make an observation?
You may.
Basically, the thing is, and I agree with you, your bang for your buck for Earth-based is really compelling. The thing is that there are things that we can't do on Earth, and that's the infrared stuff, and that's why we did JWST.
Yeah.
And I guess the thing is whenever we can, we're going to need to do it on Earth for the best bang for the buck. And if we can't, then, well, there's always space.
Well, there's best scientific bang for the buck. So that's an important distinction. You're right about that. We can learn more. So when we look at all of the things that all the telescopes can do and we group them up, ground-based telescopes can do more in aggregate than can a comparable space-based system. But we're in agreement on the fact that we absolutely have to have space telescopes for certain things. We cannot look at X-ray sources here on the ground. The Hubble Space Telescope has the ability to look at the ultraviolet. JWST will not have that capability. So when Hubble finally dies, we have no way of looking at the ultraviolet part of the spectrum in the universe. That's a big loss. We could never hope to get that here because, well, UV doesn't get to the Earth, thankfully. Otherwise, we'd all be cooked. So, but it's an important wavelength to understand the life cycles of stars and the compositions of stars, things like that, as well as star forming and just all kinds of reasons you want to look at the ultraviolet. That's going to go away with Hubble, and nothing is coming along that I know of except for LUVOIR to replace it. LUVOIR, its name stands for Large Infrared Optical. Let's see, Large UV optical and infrared space telescope. So it's going to look across a huge range of wavelengths. LUVOIR will be better in that regard, way better in that regard than JWST. It'll be bigger, have larger resolution capabilities, and a wider wavelength range than what JWST has. So, so yes, no argument for me on that. Space telescopes are vitally important, and they just some things we can't do without them. So, Architufus, I'm going to read yours because you agree with me. Earth telescope is better because it's cheaper, so we can make thousands of them instead of relying on one really good space telescope that only a few people can use and can break at any time. Yes, well said. Hi, Michael from Copenhagen. Welcome. I'm glad to have you here. I'm in Austria. Service from Australia. Thank you for joining as well. I'm way back up in the chat now. It takes me back to "We Miss You, Pluto" from your ultra deep field video. Yeah, I know. I may make a t-shirt of this. I saw a license plate frame the other day of a car in front of me that said Pluto from 1930 to 1930 to 2006 when they declassified it. It's not dead. It's still there. It's just not a planet, and I'm okay with that. I don't care what we call it. It's still there. But yeah, we'll miss you, Pluto. Let's see. And the comment from Charlie. We all actually, reflectors have issues also, as the slope error produces a large issue, bigger than for refractors. Yes. But there, I would argue that the problems associated with reflectors are mitigated compared to, or a lot less anyway, than what you get with a comparable refractor. Could you imagine building a 30-meter piece of glass? I don't think it can be done. It has to be perfect, right? It had to be a perfect piece of optical glass that didn't have chromatic aberration in it, and so color correcting that sucker would be a real problem. And this is from Raj. Each have their own advantages and disadvantages. For example, ground telescopes, you can fix them easier if they break. Build them almost any size. Space telescopes, you do not have to think about with Earth's atmosphere, and can place them at different locations. So yeah. All right. Also, this is from Charlie. Reflectors are an issue for chronographs, usually much more backscatter than forward. That's a good point. So chronographs are this ability to block out the light of a star, so that you can see the surrounding region, which are usually very bright compared to whatever it is you're looking at around it. And so let's see. Stingy McStingy Pants Face. Hello from Australia. Welcome. Boy, it's early in the morning for you. So welcome. Thanks for getting up. Enjoy your coffee. Sarah, yeah, thank you. Power and all in Chile. Thank you, Juan. I had a brain fart there for a minute. Saturn's back. Hello, Saturn. It's good to see you. Love your rings. Of course, this is from Charlie. This is only true if your optics are diffraction limited. Not easy for large objects. Yes, but it's getting, I would say the capabilities of building these optical elements now are getting better all the time. Raj is commenting, I would say in the past, ground-based telescopes were better in terms of cost and ease of assembly, but since cost per launch is getting less expensive and launch vehicles are able to lift more payloads, we might see more space telescopes at different configurations and locations. Yes. Yes. Earth versus Space Telescope sounds like an awesomely dumb sci-fi B movie from the 50s. The attack from the space telescopes. Yes. Galaxy is commenting. So in the large radio wavelengths, where the graph is brown, we have no view of the universe, no telescopes on the ground, and none in space. I wonder what we're missing. Yeah, that would be shorter than, or longer, I would say, than microwaves and a lot of the radio wavelengths. Yeah, that's a good point. It is opaque down there. We're talking kilometer wavelengths, though, right? Really long ones. I don't think the Very Large Telescope with 4 mirrors is ever built. Yeah, the Very Large Telescope, it exists in Sarah Paranal. ESO is operating it right now, and of which the HARPS instrument is a part of it. So yeah. Hi, Cryptolicious. It's good to see you. And Charlie is commenting, Vera Ruba is Baker Paul 3 mirror, is a Baker Paul 3 mirror buried focal length surface design. I know, it's really crazy. I wonder if I can find a picture of it. Let me see. Let me see here. I don't want that. I want this. Okay, let me see if I can. Oh, that's a. Let me go here. Let me open up another tab. Let me say LSST primary. Let me see if I can bring this up. Put this on. And yeah, let me see if I can find a schematic here. I mean, here's a picture of it. This isn't very good. I want to see. Let's see. I want to see gallery. Oh, come on, really? I just want to see the thing, man. All right, let me select all. I'll trust you, Vera Ruben, with my cookies. Camera optics. Mirrors. I want want to see if there's a diagram that shows the three. I won't take up a lot of time, I promise. I just want to see if I can. But he's right. It's got three mirrors within one. One is wide field. One of them is large. There are two different focal lengths built into the same primary. I just want a schematic. That's all I want. We go Vera, Ruben, primary, schematic. You can't really see it. Let's go way back to when it was lsst.org. No, I promise I'll stop in just a minute. Poop. Oh well, okay. I can't. Sorry, I won't waste any more of your time. But I was hoping to find a schematic of how this thing looks, but I can't seem to do it. At least I should have. But it is an amazing primary. I've never seen one like it. Galaxy is commenting, I can imagine that we would put a space telescope in these very large radio waves. They would say a whole new window on the universe opened up. That's right. That's exactly right. E-Bone. So I think that the best telescope is the one that is available. Technically speaking, for X-ray, UV, visual, and IR space telescopes are better. Radio and in some visual spectrum, Earth telescopes can do very good indeed. Yes, it's hard to argue with that. And Galaxy is commenting again on the radio spectrum. And who knows? Civilization is communicating in these large radio wavelengths. Just saying. That's right. You never know. We can't be looking in those wavelengths. But let's just take a look. Let me go back to that slide. Let's see. Where is that slide? Here we go. All right. So if we go back to this, these are greater. This is like, what is that? That's 10 meters. That's 100 meters. So 20 meters ish on down to a kilometer. I don't know what would be out there. But that's pretty long wavelength range. But yeah, you could be right. Could be aliens communicating back there. We just don't know. That's a big swath of radio though, right in here. So, you know, this area here is pretty good. It's amazing how we make everything work right in this rocky region between about 100 nanometers and about I don't know, 5 microns. It's really where a lot of the bread and butter of astronomy is done these days. Sadly, let's see. This is from Stakra. Sadly you can only measure the 30 meter ELT and the QWLE Arecibo and fast in tennis court. That's right. Isn't that weird that the unit that we that we measure telescope area in is in telescopes or is in tennis courts and basketball courts. Soccer pitches, I guess, are too big. Yeah. How many tennis courts is that telescope? I can't think about it unless you tell me in tennis courts. E-Bone, on the other hand, I don't consider space telescopes overwhelmingly expensive. On the contrary, again, compare the cost of JWST to a regular bomber. Well, okay, it's more than a regular bomber. It's as much as an aircraft carrier. Okay, that's the price. The United States spends about $9 billion, $10 billion on an aircraft carrier. And this is one of those. This is one of them. Now, I don't care. I mean, I could care less if it costs $20 billion. I think it's worth building and putting up there. I don't care. It's a good use of taxpayer dollars as opposed to building an aircraft carrier, but that's just my opinion. I'd rather have that than an aircraft carrier. Although I do think that somebody somewhere is corrupt as hell. That's all I mean, come on. Who the hell? Some people made a lot of money on the JWS in Northrop Grumman. Made a lot of money on the JWST program. Cost plus contracts they must be delightful for a company to get from NASA. Cost plus means that they aren't held to any deadlines and cost overruns they don't have to pay for. So they get more money. So the risk is very low for a company on a cost plus contract. So JWST is a complex telescope. This is from Raj. Especially, it is the first of its type. Yeah, and that's what I tried to point out. I mean, while we do try to be as conservative as possible, we meaning them. I don't really design space telescopes. As using space qualified hardware, because you don't want this thing to go up and not work. There is a certain amount of innovation that has to go in it, and most of that innovation is in detectors and cameras and spectrographs, things like that, because they that's where that's where the science is going to be, right? So you need to design certain things to work at certain wavelengths because you want to see certain things. But things like an aircraft or a spacecraft bus, or what nuts and bolts and stuff to use, or hinges and all that kind of stuff, is pretty much set as far as qualified space hardware. The exception with JWST, of course, was with the beryllium that was used to make the primary mirror structure with. So that was new. Those were lightweight, and of course, using gold on the primary mirror surfaces was also important, because it needs to reflect infrared radiation, and that's the kind of coating you need for that. So it's not a lot of gold. I mean, I know JWST probably is worth more than its weight in gold at this point, but the amount of gold in there is about it's like 5 atoms thick or something. It's not a lot of gold. I think it's like less than what you would see in a wedding ring. And so let's see. Vera Ruben is a very existing telescope. Yes, it is. It's going to see first light here, I think early next year, or maybe this year. I don't know. Yeah, it definitely exists. It's Vera Ruben's out there. It's going to happen. They're getting ready to start first light very soon. The E-bone, the problem I see with space telescopes is their lifespan. Yes, and that's going to be a bigger issue now that we can't go up and repair them. JWST is designed to last for 5 years. Probably it'll be up there for 10, hopefully longer. But there's no repairing it. There's no repairing it. Raj Luthra, yes, at the moment their lifespan will be lower than a ground-based telescope. And Charlie is commenting, very true. This is from Stikra, a large imaging survey. Still, if you look at the instruments, I think you were referring to Vera Ruben. Still, if you look at the instruments on most ground-based telescopes, they are dominated by spectrographs. That's true. Not entirely, but there's a lot of spectrographs out there. Raj Luthra, but that could change when space. Okay, I already read that one. Okay, now I'm getting to where I was. VLT, OLT. I think you mean VLT. Would have resolved down to a million. I don't know what OLT is. Okay. We already talked about LUVOIR, E-bone. Now we are not taking into account the thousands. Okay, we already. Sorry about that.
OLT is overwhelmingly large telescope.
Oh, that's what. Yeah. Sorry. Thank you. Yeah, the overwhelmingly large telescope. Thank you for that. Yes. It just keeps getting more ridiculous. Super huge, super ultra mega telescope. Let's see. Bullshit vendor. Astronomy Cast recently did an episode about orbital occulters, space-based star shades for ground-based telescopes. Seems to give amazing results. That's right. I didn't even get to that. Star shades are these things that they want to launch in orbit. They're going to be designed for things like I forgot the name now. It's one of the 4 projects that is being considered in the Decadal survey. Anyway, star shades are these things they look like daisy petals, and they unfold and they block out the light from a star, and they can be used to image directly exoplanets. And they're all kinds of. They're basically a big occulter, and they can be. They do have plans to use these for ground-based telescopes. So that's a good point. Also, no launch vehicles, even SLS-2 and Starship can't get telescopes the size of ELT off the ground. The size of the firing limits the size of the mirror, even with Webb-style folding. Well, LUVOIR, Webb is folded once. It's folded back once. LUVOIR is going to be folded back twice. But you're right. Sooner or later, you're going to reach limits on this. Is anyone really talking about resolving exoplanet surfaces? Yeah, man, I'm telling you, this is something that can happen. We can do this. And that's amazing to me. when Svetlana told me that, and she showed me that, I mean, so to prove that it worked, she imagined the signal of the Earth going through an exolife telescope mounted at a distance of where Alpha Centauri is. And so they ran that simulation, they created that simulated signal, and then used the algorithm to deconvolve that signal into what you saw in that slide. That's crazy. That's crazy. The fact that we can do that one thing is like, it's worth it to me. That's worth the price of admission. Kyle on YouTube is asking, are there any current programs working on actual sunshades to help block out stars to view exoplanets? I understand some concepts have been done, but any actual programs in the works? Well, yeah, there's the one that, so no one's going to build anything until they get the funding for it. And so if depending on what the decadal survey decides, which is going to be early next year, I think now, there is, I need to remind myself what they are. So let's see, decadal survey missions. Let's see. Sorry, I'm going to take a quick minute here and see if I can find it, because I'm having a moment here. Or I can't, for some reason I used to have those. See, there's links. There is that's the X-ray telescope. There's LUVOIR. There is oh Christ. There's two more I can't seem to. I have to search my own YouTube channel to get, because I did several hangouts with each one of those missions, and the one that is looking for exoplanets is going to have the star shade. Okay, that's the one that will have the star shade with it. LUVOIR, there's a LUVOIR Lite, and there's also, I think, LUVOIR with a version that has a star shade in it. But these star shades can be built. No one's actually built one and deployed it yet because no one's paying the money for it, but it can be done. So so to answer your question, they're ready to work on actual star shades, but they haven't done it yet. Could a space telescope, this is from Dan from Canada. Could a space telescope be built in stages? You mean launch a certain part of it and then build it later and go on? Yeah, that could be done. But I think the infrastructure needs to exist first. And I think that's where things like the NASA Gateway comes into play, right? The NASA Gateway is this thing they want to build around the moon that is between the Earth and the moon, and it's a platform that we can do all kind of things with. And so I think a space platform of some kind would be very helpful to building things in stages. But I mean, right now, let's look at the launch capabilities we have. We have what SpaceX has. We have the SLS, kind of, sort of, maybe at $1 billion and plus a launch. But all of it's got to be robotic, because the human capability to get out there right now only exists in low Earth orbit. I mean, the Inspiration 4 mission that came back last weekend went to the highest low LEO orbit you could go to. It's a little bit higher than the space station, but that's it, right? I mean, after that, we don't really have any capability to get any further out with human beings, so it'd have to be robotic. And there are companies working on robotic stuff, like to fix satellites and telescopes that are already in space, or to help deorbit them, things like that. But our capability is woefully inadequate at this stage right now. This is from Neil. Tony, if we can see galaxies from billions of light years, why can't we see planets from, say, 10 light years? Well, because they are very dim, like, was it thousands of times dimmer than their host star, right? And so the host star is obliterating the signal from the reflected planet. That's why when JWST launches, they've got these micro shutters, and these are little windows that open and close over the detector. So if you've got, say, Alpha Centauri in the frame, you can close all of the little shutters that are where that's letting in the light from Alpha Centauri, the star, and block it out, and then collect the light without blowing out the detector, the very, 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 very faint and dim exoplanet that's right next door. So that's why we can't see them directly yet, but we can because of that. And that's why occulters and chronographs are very important in space telescopes these days. But we can infer their existence, and we do that in one of two ways right now. We look at the planet as it goes in front of the star and dims down a little bit, because there's a dimming there, we go, there's probably a planet in there pointing or dimming out that star. And from that information, we can tell how big around it is, and we can tell how fast it's going around the star. Because if we see these dips at a regular interval, then we can get an idea of the orbital period. This has a bias, though. And the bias, the observational selection bias, is that we tend to only see planets that are very, very close to the star because we don't stare at them long enough. You would need to stare at a system like the solar system for over a year. In fact, for up to 10 years if you want to see other planets like Jupiter, Saturn, and the outer planets as they transit the sun to get, and you need to do it for more than once so you can get an idea of its period. So you need to do this for a really, really long time, and other things that space telescopes just aren't very good at. We can't afford that kind of time to look at them. So what we tend to see with things like TESS and Kepler before it, Kepler was up for 5 years for a reason. It was up to it stared at that one area of the sky in Cygnus for 5 years precisely because they wanted to get as many transits as they possibly could in a given system. And so that's one way we can see what's around a star. And the other way is what we just talked about, radial velocity, where you look at the spectrum of a star and you see that spectrum shift as the planets that are in orbit around it tug it around and pull it with their gravitational pull. From that information, you can learn how massive the star is, as well as its period, and well as how many of them there are. You can do it from the transit method too, find out how many there are. It's just pretty complicated, but they can do that too. So, but that's the only way right now that we can see exoplanets. So be careful when you hear astronomers talking about things like, this is an Earth-like planet, could have water. They don't know. All they know is what I told you. They know the size and the period and the mass. That's it. They don't even know if it's got an atmosphere. And the careful ones will say, if this had an atmosphere, then it would be, and it's at a location from its star such that it could have liquid water if it had any. So be careful how you read these press releases, because it's very easy to think, oh man, they found an Earth-like planet that got water on it. They don't know. They don't even know if it has an atmosphere, right? So we got to be careful with this stuff. Okay, so let's see. Here's a questione. Tony, why can't crypto NFTs of the first exoplanet photos be pre-sold to fund exoplanet projects like ELF? Like you said, traditional funding is slow. I don't know. That's not a bad idea. We should talk to Jeff about it. Say, hey, and the other members of the team, and say, hey, man, you guys should put out some NFTs and sell some crypto for several redonkulous millions of dollars. The things that are being sold right now for NFTs are pretty stupid. So this would be at least a good like the first light from something. If you could get a first light image, that's not a bad idea actually. If you could get a first light image from, say, the Dark Energy Survey, the DCAM, the first image of whatever DCAM took, and made that into an NFT, that'd be a money raiser right there. Something scientifically useful, right? The exact image I guess it would be a time series of data. I don't know what gravitational wave data looks like. It's not an image, but whatever it is, imagine the first gravitational wave detection of merging binary black hole or merging black holes as an NFT. That might raise some serious cash too. I don't know who's spending money on this crap, but somebody is, and it'd be good to use it in a good way, and that's a good idea. Now you got me thinking, what else could you use? The first image from the Viking lander on Mars. That'd make a good NFT, wouldn't it? These are actual data. The data still exists. I mean, that's the thing I don't get about NFTs. Even though you've bought the NFT and you own it, you don't own the rights to it. You don't own the copyright to it. And the data still exists. So it's not like you're owning the data and nobody else can study it. So I don't know. Why not? It's a good idea, man. Using NFTs to fund science. Let's make a hangout on that, because I need know more about that than I do. Excuse me. Let's see. Neil Knight, maybe because the planets are not quite visible due to light of their stars. Yeah, I think we just talked about that. Charlie is commenting, sky glow is another problem for ground-based, even on dark skies. Yeah, that's true. All the problems with ground-based telescopes are with the atmosphere. A lot of that sky glow can get filtered out, though. So with big enough diameter objective, you can get the signal from the noise pretty well. Space telescopes, this is from Tolu, space telescopes may become much more cheaper than Starship. Build some telescope starships with a 9-meter wider mirror and just land them for technological updates and launch again. Maybe you're just dreaming. Nope, that sounds like a good plan, man. Let's do it. You have any contacts to Elon? Let him know. Jim, it's good to see you, James. Good day. Also from Australia, if I'm not mistaken, because they are tiny and shined out by stars. Yeah, okay, we talked about that. Let's see. Zach says he enjoyed the debunking terraforming on Mars. Man, I got some mean responses to that thing. I get that I was negative. I know I was a negative Nelly. But was I wrong? No. It's like I admit I don't have a lot of faith in humanity right now, and I don't see it getting any better. But I would love to see an example of where we have solved I posted that question to Charlotte last week after I did the stream. I said, I was talking about this and how uncomfortable I was giving my opinion. And I said, she asked what the stream was about. And I said, well, I was talking about terraforming Mars and I posed the question, can anybody give me an example of a global humanity-wide problem that we've actually solved? And without a pause, she said, smallpox and polio. So there you go. The thing about that, though, is that we did get together as a species and get rid of smallpox. It took generations to do. Smallpox is finally eradicated from the planet, as is, I think, polio, although there may be a handful of cases left in Africa. It has been largely eradicated, and it was done in a way that wasn't that was more or less altruistic. We did it because we needed to get rid of smallpox, but it took generations, and we did finally get there. It took a long, long time. So what worries me about the problems that we're going to face as humanity in the future is our technology is going to get more and more advanced. We're going to have things developed that will give us smaller margins for error. We can't screw it up. Nuclear weapons are already one of those developments where we don't have a lot of room to mess around. Right? We can screw that up really, really easy. And so we're on a knife's edge with that. So it's like as more and more technology gets advanced, we may not be able to handle it, right? And that could be a great filter. An example I always give is social media. We invented social media. It's a great thing as far as it went, and then it turned into this really a weaponized thing against each other, right? And now it's become more malevolent than benevolent, in my opinion. So these are examples of what I'm talking about, where technology has these unintended consequences, and the way social media has evolved is one of those things. But thank you, man. I'm glad you enjoyed it. I felt nervous as hell doing it. I promise I won't get that negative again until I talk about JWST. I'm kidding. I won't do it for JWST either. Life in the Universe, on the other hand, if we ever have one of those hangouts, you might get a little bit more of it. But thank you. I really appreciate that, Zach. It means a lot because it was scary. Charlie's saying, I don't think there are any space-based spectrographs that are stable enough to be used to find planets. Well, JWST is going to have them, so it'll find planets. HARPS is on the 3.6 meter telescope in La Silla. Oh, apologies. I thought it was in the VL, part of the VLT. Is it Symphony? What's on the VLT? Something is on the VLT that has radial velocity capability, but I don't know it off the top of my head. Sorry, was it Austria? I saw Austria. I scanned it, and I may have said Australia. I apologize. It's if you're from Austria, I know the difference, even though I didn't act like I did. I saw it, and it was quick, and I scanned it, so I apologize. Space telescopes are better, more to see. Okay, fair enough. So let's see, and it's from Architufa. So there's nothing Elon Musk can do except for maybe pay for the telescope cost. Yeah, just because your ride is cheaper doesn't mean the telescope is. That's true. I think the $9.5 billion didn't include launch costs or operational costs either. I think it was just to build the thing. So the LSST is actually a single piece of glass that is both primary and tertiary mirror. I know. I wish I could show a schematic of that. It's really cool. That's really you look it up. What they can do with that telescope. It's really amazing. Never before has anything been built like that. So let's see, Tony, whatever happened to the 8-inch CubeSats that were being designed by a sister company to OPT? I forget the name. The name was Space Fab, and as far as I know, they're still building those. That one of the business models they had for it was they were going to allow you to take space selfies. And as you can imagine, countries had a real problem, especially the United States, with anybody pointing an 8-inch telescope from orbit down to the ground. So I don't think that capability is going to make it. But there should be where you pay via an app on a phone for telescope time on one of, and they're planning on building several. These are 8-inch, 20 centimeters or so space telescopes that will be available to anybody, everybody, to do whatever you want. And you will interact with it via an app to get telescope time, pay for telescope time. It's not going to be a lot of money either, from what I remember. I think they're still on board and still doing it. I should talk to Dustin about that. We should have them on Space Junk again and get an update. Let's see. Third Rock is saying space telescopes are better than Earth scopes because they are truly diffraction limited. There's a lot more to life than diffraction limited, man. A lot more to life. Starship this is from Forlaren. Starship makes terrestrial satellites obsolete. Before Starship, money is best spent analyzing the data we already have. Pragmatism never wins, so I'm not holding my breath. Before Starship, money is best spent analyzing the data we already have. Yeah, I suppose Starship does make terrestrial satellites obsolete. Yeah. What about gravitational wave telescopes? Well, the only one we have right now, at least the network of ones we have right now, are ground-based. LIGO is a network, and I think it's Vista. Is that the other one? Anyway, they're located. LIGO is in Washington, and the other one is in Louisiana, and then there's one in Italy, and I think there's another one somewhere else. Anyway, this is a network of ground-based laser interferometer ground observatories, LIGOs, which detect gravitational waves. However, if we were to look at LISA, the laser interferometer space antenna, that's going to be 3 antennas spaced 50,000 kilometers apart, that will be able to see supermassive black holes and all kinds of other gravitational wave things that we can't see on the ground. I'm going to do a hangout on gravitational wave observatories, how they're configured and what wavelengths they can see depending on their configuration. But that is also a very good use of both ground-based and space-based telescopes. I still think ground-based holds its own there because right now we've got proven data from one of those. But just because of the fact that you need such a long baseline for seeing the larger larger black hole mergers, you need 50,000 some odd kilometers. That's harder to do on a curved surface like the Earth, so you need to be out in space to do it with. But it's just a practical consideration, not a technical one. You can maybe, I don't know, somehow raise them up high enough that it overcomes the Earth's curvature and do it that way. But no, you can't because 50,000 kilometers is pretty big. So that's an example then of something that you need space for. Lisa. Very long wavelength would be interesting, but it would be difficult to get much resolution. Remember lambda over d. That's right. Thank you, Charlie. That's a good point. Just do that little relation and it tells you the angular resolution that you get. Divide the diameter in meters by the wavelength in meters and you get a number, or you divide it into a wavelength in meters and you get a number, a dimensionless number in radians. That's your angular resolution. The sad thing about JWST, this is from Tolu, is that there will be no more development. It's like Space Shuttle, but very, very nice, but expensive. The Space Shuttle was also once developed, and then there was no more improvement. Yes, and the space shuttle never really lived up to its ideal of making space cheaper, did it? It just kept getting more and more expensive as the program went on. So, but boy, do I wish we had the space shuttle now or something like it to get us out there and repairing stuff. It really brings home just how to use a telescope for space telescope for 30 years. And being able to repair it's pretty nice. Now, alternatively, I've mentioned this before, SOHO, which is at the L1 point, the Earth Sun L1 point, has been up for also the same. It was launched 5 years after Hubble 95, and it's still up there doing its stuff. It's got the LASCO coronagraphs, which I'm sure you've seen data from, L1 or C1, C2, and C3. C1 is down, but C2 and C3 still work. Yeah, so it's possible to launch something and have it be up there for 25, 30 years. So yeah, that's pretty good. So let's see. Don't fold, says Tolu. Get 5 Starship telescopes and with 9 mirrors each and bind them together for a big scope. Okay, man. You like the starships, don't you? Architufus is commenting, yeah, SpaceX / Tesla can do it because they're all in-house production. The problem NASA has with cost is the thousands, this is hyperbole, of subcontractors required just to get a single spacecraft built. Yes. And Charlie is commenting, Christy, the area disk for an optic is proportional to the wavelength divided by the aperture. Big wavelength, low resolution, unless you have a really big primary. Yes. I didn't want to go through that math, so I'm glad you guys are doing it in the chat. Third Rock, so thank you for, that sounds like a Tycho Station, if you ask me. And Kyle is saying, thank you for taking my question. Dude, that's why we're here, to do this. This is a stream. We're supposed to chat, interact. Otherwise, I just make a video and post it, and you guys just have to watch it, and that would be that. So Pyro, welcome, by the way. It's good to see you back. Was the in-airplane telescope discussed yet? Oh, Sophia, the one that's in the telescope that's in the 747. No, that hasn't been discussed yet. That's infrared, I believe, right? And it is still going strong. It's neither ground nor space-based. It's airborne-based. I think there's a lot of technical issues with that make it practical. I mean, yeah, it's good for short observing runs. And it would not be a good idea for any kind of survey. So it's a bit limiting. But for what it does, it's a good telescope. So, yeah. So that, yeah, you're talking about Sophia there. Wouldn't it be better if certain billionaires invested in the ExoLife Finder instead of launching themselves into space? 150 million isn't expensive, and I'm somewhat surprised it hasn't been funded yet. Me too, actually. I mean, SETI got a big infusion from Greg Allen. The Allen Telescope Array is named after that Microsoft guy. He's a billionaire dude. And he gave it to SETI to do that. But I agree, man. I feel like we need to have like a Jeff Bezos ExoLife Finder or something. Just give the guy $200 million, whatever it takes. And it's not, he spends that on lunch. So yeah, I agree. YouTube is here. Hello, YouTube. I've got some issues with you, man. I got a lot of issues with you. Okay, so Third Rock, it's just like asking, why did it take so long to discover the Higgs boson? I don't think I missed the first part of that. Better and Better is here. Welcome. It's good to see you, man. So let's see. Already at 1.8 billion in annual sales of CryptoPunks, silly 8-bit style JPEG doodles. Exoplanet photos seem way more valuable, historical and collectible. I know, right? I mean, you're onto something here, Crypto. I'm thinking about this. Not a bad idea. If you could spend billions of dollars on a stupid ass 8-bit thing, then man, just buy the first data, first light of something. I think would be worth first light of the Hubble Space Telescope. Nah, maybe not because of the spherical aberration. But still, no, that's historical, isn't it? Hysterical. Should do it. All right. Third Rock is still wanting to convince me. Space telescopes are better than Earth-based telescopes for one reason. They are. Oh, we already read that. Cryptocurrent equals climate change propellant. Currency is yes. Let me do this one. Cryptocurrency equals fuel to the fire that is climate change. Well, there is that point. She's talking about Bitcoin, I think, the amount of energy it takes to mine Bitcoin. But NFTs are based on Ethereum, which is going to a proof of stake model instead of a proof of work model, which is, I'm told, going to be orders of magnitude less damaging to the environment than Bitcoin is. So, but you do bring up a good point. Not great for the environment. Bitcoin. I've been around 3 large telescopes for first light. The images are not really all that interesting. Sometimes they're really bad. I know, but that's the point, right? It is the very first photons to fall on a detector after years of development, testing, and funding. You have this really crappy image of a star, out of focus probably, full of cosmic rays, whatever it is. But that adds to the historical value of it, right? So I don't know. I think that's a plus. I think that's a plus. Yeah. So I think we're onto something here, folks. Science-based NFTs all the way. Let's do this, man. I think I just did. We're talking about Sophia, I believe, Pyro, if I'm not mistaken. Have we addressed CFCs and the ozone? How we address CFCs and the ozone? Yeah, we talked about that. Do you talk about one example of humanity solving problems? Yeah, that's always the one that they put out from a science perspective. But I respond to that by saying that was a no-brainer. That was easy. We had easy solutions. It didn't cost any corporations money. All we had to do is stop putting CFCs in propellant cans, and it went away. And it was an easy fix. But you know what? Guess what's coming back? The ozone hole. So, did we fix it? I don't know. Maybe you should do a live stream on the benefits of terraforming Mars to balance the subject. I don't see any benefits. You can't do it, first of all, so I'm not going to talk about the benefits of it. Okay, so yeah, I think I'm sorry. I think I'm behind in the chat, Pyro, so I'm sorry. I'm getting caught up here. Social media is a great thing. No, it never was, just like mobs. That's right. Did I say it was a great thing? No, it's an unintended consequence. It started out with a lot of promise, and now it's turned into a weaponized sort of knife edge problem for humanity to face. It's going to, if anything's going to bring us down, it's going to be each other on social media, man. That's a great filter if I ever saw one. Let's see. Hey, let's see. This is better and better. Yeah, I cleared his comments after thinking about it. If it was better to leave them or delete them. In the end, I went with delete because his comments after that didn't really add anything constructive. Yeah, man, don't. If anybody's irritating, saying stupid stuff, get rid of them, man. I don't care. You know, not all opinions are worth hearing. And anything we invent or discover can be used to do good or bad things. It's just a matter of choice. That's right. And so my point in this is that whatever we invent tends to have a negative outcome in the long term, right? And we don't have this ability to. I'm not going to do it. I'm not going to do it this year. I'm sorry. Don't get me into that again. I'm not going to talk about this. And James Dugan would like for you to give away some valuable personal data by hitting the like button. It helps Tony with the U-Group algorithm he likes so much. That's right. So please, let us all give to YouTube at all some of our valuable private data so that they can better sell us things. And somehow Deep Astronomy benefits. I honestly don't know how it does, but apparently I benefit somehow. So let's see. Where's the best place to ask questions? Well, this chat is one, but the funnest is if you go on the Discord server and go in the live stream voice channel and talk to me. If you just go in there with a microphone, I'll hear you, and your voice will go into the intertubes. It will. That's what Tony was doing just a while ago.
Guaranteed, it's much more fun.
Yeah, there. See, much more fun.
So I can open my mic right now and comment.
You may say who you are.
Okay, Rami Imad from Astrogate. I've
Oh, yes.
participated before with you and really liked it so much.
Good. Well, welcome back. So what do you want to say?
Uh, I want just to say one tiny comment here that the echo chamber effect from social media algorithms and AI, in my personal opinion, will be the great filter coming to solve the Fermi paradox.
That's right. Yes, I think I agree with you. There is this. The more we hang out in these echo chambers where we only hear opinions that agree with our own, the more we start to think that whatever we think is the truth. And regardless of whether it actually is or not, it doesn't matter. And we tend to go through life thinking these thoughts about how great we are or how right we are, with this complete inability to accept someone else's point of view. And it become very tribal, and it escalates, doesn't it? It ends up going out into the real world. We've seen that happen many, many times, where people think a thing is true online, and then in real life act on it when it isn't true. And human beings have so many biases that are detrimental to our survival, that if we don't learn to recognize and deal with these, it's going to be the end of us. And there are some things I don't think we can get past. We don't. I use climate change a lot. People are optimistic about our being able to solve it. I don't see how. I don't see what we've done to do anything about making it better. Yeah, a few of us, a distribution of us, are concerned about it, but the people that matter aren't, and no real change is coming forth. So, and yet we know the problem is there. We acknowledge, at least most of us do, that there is a problem. Not all of us have to agree that it's a problem, as one of the commenters pointed out in the last video. I agree. However, enough have to agree that we are going to do something about it. And we have yet, even with everybody got all super hyped about the Paris Accords, and yet not a single country has put forth a plan to do anything about it, to meet the goals they committed to during that summit. So we know the problem exists, but I promise you, we're not going to do anything meaningful about it until after some major catastrophes have occurred. That's what we do with everything. And there's some problems that if we wait too long, the margin for error is too small for us to overcome, waiting around and being in denial, or trying different paths. Some paths are deadly and we can't recover from. The margin for error is getting tighter and tighter the more our technology advances, and we better get some wisdom to go along with it at some point, or it's going to do us in. And my problem is that I think we're very capable of inventing and designing our lives in whatever way we feel like, but we have a real deficit when it comes to dealing with any of this stuff with any level of maturity.
Yeah.
We don't get
Hey, Tony.
Yeah.
So my thought on it is that.
Oh, I think he disconnected.
Oh, did you drop out? Okay.
He disconnected. I don't know what happened.
Yeah.
But okay, he's back.
That we are ruled by our emotions and our tribal instincts, where we don't really apply rational thought. These are gut instincts that we employ.
Yeah. And I mean, I could do this forever, but I really, it's a little bit off the topic today, but yeah, I mean, I agree with what you're saying on that. I just don't want to go any further because I'll get negative again, and I promised myself I wouldn't do that in this stream. So, but you guys make great points. You guys do, and I stay away from YouTube. I mean, I started this channel in 2006, and there would be entire years, 2, 3, 4 years, I would do nothing on this channel. Then I'd come back and do stuff on it again. Because there's this ebb and flow of it just gets to a point where inevitably it gets to be too much for me to handle, or it starts to grow a little bit too fast for my liking, and then I pull way back and stop making content, because most of the content I make tends to bring out this kind of discussion in people. And I just, engaging has been really hard over the years. Okay, so
if you would allow me just to shed light on the bright side.
Go ahead, man, and that's where we're going to go.
Yourself,
Uplift us.
Yourself and people like you spreading awareness are actually doing something, are actually trying to save us all. So I really thank you for this. And
bless you, man.
Everything here is only a symptom for the real problem, which is, in my opinion, it's the echo chamber effect. It happens in the vaccines, it happened in everything else, and scientists and science promoters managed to convince so many people and save so many lives by convincing them and explaining how vaccines work, for example. And the same can be applied to the climate change, the same can be applied to all other problems. So there is some hope yet.
Okay, good, and we'll leave it with that. But that message of hope, that we can, I'm sorry, I'm reading the chat and got distracted. So I'm going to go ahead and stop the chat there, guys. I think I've gotten through most of your comments. Pyro, I did talk about Sophia, so I hope you heard that. I don't think, by the way, that there are any more observatories like that in the works. Airplane-based observatories have very special use cases. So I don't think there's any more like it coming along. So, but it is a cool telescope. You're right about that. All right, guys, I'm going to go ahead and sign off on this live streaming stunt. I want to thank, so Rami, thank you for joining. Tony, also on live stream voice channel. Consider doing that next time, folks. It's a lot of fun. And it's easier for me just because I don't necessarily miss people's comments, and also I don't misread them like Austria versus Australia, right? So I get it right. So thank you very much, and I will see you guys next Thursday, where we're going to be talking about, is JWST too big to fail? And I'll have an answer. I won't just, it's not clickbait like this one here. I also answered the question. So thank you all for tuning in, and on behalf of all of you guys who participated in the chat, thank you so much. I'm Tony Darnell. Thank you for watching, and as always, keep looking up.